All right, babies, welcome to our last video lesson here on our unit on current electricity. So what we're going to talk about today is what's called a combination circuit. So a combination circuit is going to be a complex circuit, okay, compared to our simple circuits that we had. Why it's complex is because what we're going to see are our two different types of arrangements. We're going to see series and we're going to see parallel all in one circuit. So for example, we could have here, notice I have my wire splitting off into two branches. So because of that split, this would be a parallel circuit. So we have there parallel. But within that parallel circuit, notice here how I have two bulbs that are in series. So this would be considered a series circuit within a parallel circuit. And I can see here, okay, I got my parallel branch again. But then those two that are in parallel, notice, are also in series with this third bulb. So I could have a series set of bulbs within a parallel branch, or I could have a parallel set of bulbs within a series circuit. So this is a combination circuit because we're looking at both series and parallel all in one. Now, in order to understand these types of circuits, we need to remember our rules that we talked about last time, that each of these circuits, because of the arrangement, is a little bit different in terms of how they utilize the voltage, how they utilize current, and as well as their resistance. The big thing that we talked about is obviously the resistance, that in a series and parallel circuit, the resistance is going to create what's called an equivalent resistance. And that equivalent resistance is going to determine how much current there is, as well as how much voltage each of those bulbs is going to need. So know that in a series circuit, we said that the overall resistance simply adds together. That if I had two bulbs that were in series together, that would add 10 and 10 to give me a total of 20 ohms of resistance. And depending on whatever the voltage is that my current produced is going to be simply the voltage divided by that 20 ohms of resistance. Okay, but in a series circuit, that resistance is going to add together, which means the resistance is going to get bigger, and that's going to create a smaller current. Okay, whereas in a parallel circuit, we recognize here that a parallel circuit, that the equivalent resistance adds a little bit differently, that they don't add as just 10 and 10 to give me 20, that they add as inverses, that it'd be 1 over 10 plus 1 over 10 to give me 2 over 10. That simplifies down to 1 over 5, but remember, for my equivalent resistance, I'm going to take that final answer and flip it around again, that I end up getting 5 ohms of total resistance. So that for a parallel circuit, the overall resistance goes down, and by that is going to make the current actually get bigger, okay? Now, there are some other rules, again, we talked about with voltage, that voltage is divided amongst series bulbs, voltage is equal across parallel bulbs, current is the same through series bulbs, and current is divided when we have parallel bulbs, again, because of that split in the wire. So in a combination circuit, we're going to have to analyze all these different parts. And what we're going to do is we're going to take it step by step. So we're going to look at two examples here. We're going to look at the examples I kind of showed in the very beginning. We're going to look at a series set of bulbs within a parallel branch, and we're going to look at a parallel set of bulbs within a series. So again, we're going to have to take this step by step. So first of all, we have a 6-volt battery. We have our first bulb, which is 4 ohms of resistance, and then we have two bulbs here in our second branch, which are 1 and 3 ohms apiece. Now, to understand this, again, we know that in this circuit, our battery, we have 6 volts. So what we're going to do to kind of analyze this is fill out this table. The table, we're going to look at the voltage, current, resistance, and the power rating of all the bulbs, as well as the total. Okay, so to start off with, if we know we have a 6-volt battery, that our total voltage is going to be 6 volts. Okay, so that's important. Now, first thing we got to figure out is that once we have everything connected, obviously current is going to start to flow, that we're going to have charge flowing throughout our circuit. But the amount of current that is produced in any circuit is always based upon the total or equivalent resistance. So this is the very first thing that we need to find when analyzing the circuit, is what is the total resistance within our circuit. To do that, I'm going to utilize my rules within my different types of alignments. So first of all, here I have a 1 and a 3 ohm light bulb placed in series with each other. So know that when they're placed in series, that if I want to find their equivalent resistance, I'm going to take their two resistance and add them together. So I would get 1 plus 3, which gives me 4 ohms. So in that branch, there's a total resistance of 4 ohms. Now remember, why is that important? Is because when current reaches this junction point, it's going to split. Some is going to go to the first bulb, some are going to go to these two. And the amount of current that's going to go into each bulb is dependent upon the resistance within that branch. Now, because these two bulbs add together being in series to 4 ohms, notice both branches have the same overall resistance, which means the current is going to split evenly. We'll come back to that a little bit later, okay? But I still want to find my total resistance. So I know, first of all, the ones that are in series, that they add together. 1 plus 3 would give me 4 ohms. But now what I got to view is that I have a parallel branch. I have my 4 ohm resistance here, and these two which equate to 4 ohms. So I do have my parallel branch. So what I'm going to do is I'm going to take my 4 ohm light bulb in the first branch. I'm going to add the inverse of that to the inverse of the equivalent resistance of those series, which again is the 4 ohms. Adding those together, what I would get is 2 over 4, which simplifies down to 1/2, which means that the overall resistance within the circuit is going to be 2 ohms. So this 2 ohms that I found right here is going to be the total resistance in this circuit, okay? And this number is important for what we're going to do next, all right? And then why is that important? Is because we know that there's 6 total volts, but the overall resistance is going to tell us then the total current within this circuit. And the total current, we're going to use Ohm's law. We're going to take the voltage divided by the resistance. So I have 6 volts divided by the total resistance of 2 ohms, and that's going to give me 3 amps. So what we're going to do is we're going to take these numbers and fill them into our table. So I know that the total resistance was 2 ohms. That is not that omega symbol. There we go. I know that my total current is 3 amps. And now what we should be able to do is figure out the rest. So what we're going to do now is we're going to analyze the bulbs. We're going to look at the voltage, current, and resistance for the bulbs. The one thing I do know is the resistance already. Let's say that bulb 1 is our first one. That's 4 ohms. We have bulb 2, which is 1 ohm, and then bulb 3, which is 3 ohms. Okay, so I do know the resistance of each of them. Okay, now, based on what I have figured out, I know that from that battery there are 3 amps of current that's going to be produced. Okay? And that 3 amps of current is going to reach this junction point, and again, it's going to split up into each branch. Okay? Now, it's going to split up based upon the resistance, and here I know that because they're both 4 ohms, that it's going to split up evenly, which means there's going to be 1.5 amps in each of these branches, okay? So what I can do is right away, if I know that fact that they're going to split evenly, that I can say, okay, there's 1.5 amps here, and there's 1.5 amps there. That means there's going to be 1.5 amps that's going through the first bulb, as well as 1.5 amps that are going through the 2 in series. Now know that these are both going to be 1.5 because this amount of current has to go through the first bulb, has to go through the second until they reach this point where they meet up originally with the other 1.5. All right, next thing I got to do is voltage. Okay, so voltage, if we think about our rules, what we know for voltage is that in a parallel circuit that the voltage is going to be equal, that this bulb in parallel with these two, that they're going to have the same voltage across. But notice how this bulb is also parallel to the battery. Now why that's important is because I know that the first bulb should have the same voltage as the battery, so 6 volts. Now, that does not mean for these other 2 bulbs that these are both going to have 6 volts each. These 2 are in series. So what's going to happen when they're in series is that the voltage is going to be split up or divided amongst the 2 bulbs. So there are 6 total volts that we will have between these 2 bulbs. The 1 ohm light bulb is going to get part of those 6 volts, and the 3 ohm light bulb is going to get another part of that 6 volts. We need to figure out how many volts each are going to get. To do that, what I'm going to use is Ohm's law. And again, I've kind of already used Ohm's law, but I used Ohm's law to find current. What I can use is Ohm's law to find voltage by just taking the current times the resistance. So for example, if I take the 1.5 amps times the 1 ohm, that means that I'm going to have 1.5 volts for that first bulb. Okay, so that one I know is going to have a voltage of 1.5. And then if I take here the 4 ohms times the 1.5 amps, and again that current would go through that bulb as well, the 1.5 amps. If I take the current times the resistance, that's going to give me my overall voltage, which in this case is going to be 4.5 volts. Now what's interesting about those two numbers is that 1.5 and 4.5, if you take these two values and add them together, notice that that's going to give you 6 volts. And it's going to give you 6 volts because, again, these two bulbs are in parallel with this one that has 6 volts, and they're in parallel with the battery that has a voltage of 6 volts. Okay, now that I know voltage, current, and resistance, the last thing I'm going to do is calculate power. To find power, I'm going to take the current times the voltage for each bulb as well as the total. Okay, so for the first one, I'm going to take the 6 volts times the 1.5 amps, and that's going to give me an overall power of 9 watts. I'm going to do the same thing here. I'm going to take 1.5 volts times 1.5 amps, and that's going to give me 2.25 watts. I'm going to do the 4.5 volts times 1.5 amps, and that's going to give me 6.75 watts. And then lastly, if I want to find the total power throughout the circuit, I'm going to take the 6 volts times the 3 amps, which is going to give me 18 watts. Okay? Now, another neat little thing here, and this is kind of how I like to make sure that I did things correctly. The power column, in my opinion, whoopsie daisies, the power column is the important one because power is how much energy is being used every second. Okay? It's joules per second is our unit that we have for watts. Okay, so when I look at my power ratings, notice I have 9 watts for the first bulb, 2.25, 6.75, folks. I'm sorry, I made a boo-boo there. So that should be 6.75 watts. And notice my total is 18 watts. Now, why this is important is because if I were to take the wattage from all of my components within my circuit, 9 plus 2.25 plus 6.75, notice what I will get is 18 watts. This is kind of, in my way of viewing the conservation of energy within a circuit, that the power utilized by each device within the circuit, each bulb, should equal the overall power rating of the battery. Energy being supplied should equal the energy being used. So that last column for power is a good way to understand if you set up this circuit correctly. But notice within this first circuit, I use my rules of series and parallel in order to analyze voltage, current, and resistance. It gets a little confusing because there's a lot you need to think about. All right, in this last circuit, we're looking at a parallel set of bulbs within a series circuit. So you'll notice here that we have our 12-volt battery, again, which is going to produce some current. That current is going to flow through the circuit until it reaches this junction point. It's then going to split up, and half of it's going to go through the first bulb. I shouldn't say half. Part of it's going to go through the first bulb. Part of it's going to go through the second until they meet again, where that current's going to go through the third and eventually flow back towards the battery. So notice how one way that I'm visualizing how this is going to work is by analyzing current. If I know how the current is going to leave the battery and what's going to happen throughout the circuit, it then gives me an idea of how to kind of think about all the other pieces. Now know again that the current that is produced within a circuit is all based upon the voltage and the resistance. We know in this circuit that there's a total of 12 volts given by the battery. So what we need to find again is our total resistance. Okay? Now our total resistance again, what we're going to have to use is our rules. What we're going to try and do is figure out what is that equivalent resistance. So notice first we have, when the current reaches this, we have a junction where it splits off into 2 parallel bulbs. Well, I know that for 2 parallel bulbs that they're going to add as inverses. So I have 1 over 4 plus 1 over 4, which again is going to give me 2 over 4, which is going to simplify down to 1/2, which means that their overall resistance is going to be 2 ohms. But these two that are in parallel are in series with this third bulb. that has 6 ohms. So what I'm going to do is I'm going to take that 2 ohms and add it to that third bulb, which is 6 ohms, and that's going to give me an overall resistance that totals up to 8. So my resistance here is going to be 8 ohms, okay? Now, based upon that, we can then find the current produced in the circuit by taking 12 volts divided by 8 ohms, which would give me 1.5 amps. So that is my total current. So notice how I'm filling out the totals right away just by analyzing that total resistance and everything else. Now, if I just fit numbers, I know there's 1.5 amps leaving the battery. When that 1.5 amps reaches that junction point, it's going to split. Some of the 1.5 will go here, some of the 1.5 will go there. And then lastly, they're going to rejoin back up here, and 1.5 amps will go through that bulb, and again, 1.5 amps will go back towards the battery. All right, so what we're going to do then is we're going to use that idea of current to try and solve for the voltage and then the power. All right, now filling out my table, again, I do know my resistors. I have bulb 1, which is 4 ohms, bulb 2, which is 4 ohms, and my third bulb is 6 ohms. Now, with a series circuit, what I'm going to do is, again, analyzing the current, okay? What I'm going to do in this case is, last problem I focused on the current, and I divvied it up and said, okay, because the resistance was the same, current's going to split evenly. In this case, what I'm going to do is I'm going to use voltage. Okay, I'm just going to solve it a different way. Okay, so to find voltage, we're going to use the same relationship I showed in the last example. We're going to use current times resistance. So what I have here is a parallel branch within a series circuit. So what I know about a parallel branch is that these two bulbs, if they're in parallel, should have the same voltage. However, what's different about this problem is that these two are not in parallel with the battery. They are in parallel with each other. So whatever voltage these both have, they're going to share that voltage. But these two are in series with the 6 ohm bulb. So what that means if they're in series is that the voltage, the total of 12 volts, is going to be divvied up. Some of it is going to go to the 6 ohm bulb, and then the rest are going to go to the 4 ohm bulbs. And know that the rest is going to be equal amongst those 4. All right, so to find my voltage, what I'm going to start off with is this right here. I know the current and the resistance of this third bulb. So if I just simply multiply 1.5 amps times 6 ohms, that's going to give me 9 volts. So I know that there's a total of 9 volts being used from that bulb, which means then if there's a total of 12 volts, that each of these bulbs are going to have 3 volts each. Okay, now you might be thinking, wait, 3 volts, doesn't 3 and 3 add to 6? Well, no, remember there's 12 total, and if this one already has 9, that means there's only 3 left. And because these are in parallel, they're going to share that 3 volts. Now that I know the voltage, what I can then do is find the current. Now I already know the current that's flowing through bulb 3 is 1.5 amps. So what I got to do is find the current that's flowing through these 2 bulbs up here. What I'm going to do to find that is I'm going to use my Ohm's law relationship again, but I'm now going to solve for current. If I take the voltage divided by the resistance, it should tell me the current flowing through each. And notice here that I have 3 volts, 4 ohms, so 3 divided by 4, 3/4 will give me 0.75 amps. And it's going to be the same for the other bulb because they have the same resistance and the same voltage. And notice this goes back to kind of what I said before, that this 1.5, because the resistance is even in each branch, that 1.5 is going to split up evenly, 0.75 apiece. Now, is it always going to split up evenly? No, it depends on the resistance. If this resistor was larger in ohms compared to that one, that means more current would flow over here than it would there. Okay, so this is a mathematical way that I can figure it out. But again, once I figure out all those voltage, current, and resistance values, then I can find my power values by taking the current times the voltage for each bulb as well as the total. So for example, if I did 3 times 0.75, that's going to give me 2.25 watts. Same thing for bulb 2 because again we have the same overall voltage and current. And then lastly for bulb 3, if I take here 9 volts times 1.5 amps, that's going to give me 13.5 watts. And then lastly, for the total, if I were to do 12 volts times 1.5 amps, that's going to give me a total of 18 watts. Oopsies. So kind of putting this all together in total, that if you look again at the power of all three of these components, all three bulbs, you should notice again that those three numbers should add to my total of 18 watts. And again, that's a good way to know if you did this table correctly, because the amount of energy being supplied by the battery should equal the amount of energy being used by each bulb. All right, so this was looking at combination circuits. Gets a little sassy, but again, we're using our series and parallel rules together within one circuit. Okay, I'm not measuring anything. I'm using math and my ideas of each type of circuit to solve. So good luck on this stuff. If you have any questions, jot them down. Make sure you let me know. We'll see you guys.